All right, good morning. Let's get started. How's everyone doing? All right, so any questions before we start? Okay, go ahead. Right.
So what is that line we start with? Is it any line learned by a perceptron or linearization, or they learn some sets of lines?
Right.
One of the lines?
Okay, so the question is, what is that line that we're talking about? So in the last class, when I was talking about, we start with a line and then we draw the margin, that was just sort of to illustrate, right? But what will happen with SVM learning is that this line will be automatically learned using that optimization problem, right? That discussion was just to conceptualize this notion of margin, right? So how do we define a margin? So margin is nothing but two lines that are parallel to our decision boundary that sort of are at the edges of your positive and negative points, right? And the point is that, if you start with a line, I mean, this is just for the conception again. If you start with a line and then try to draw the margin, what will happen is that your margins will not be symmetric, right? Because if you fix the line, then it's not necessary that your positive points and negative, the closest ones would be equally distant from this line. That is why we say that, hey, let's first draw the margins just for the concept and then draw the line in the middle. That will be a decision boundary, right? But the margins as well as this decision line, they will all have the same W, because W kind of denotes a slope, right? Well, it's not exactly the slope, but that is used to compute the slope. Well, in some way, even B is there, right? So the main thing that you want to understand when we try to do this functional SVM versus geometric notion is that in the functional form, we say that our equation of or the decision boundary is represented as W transpose X plus B equal to 0, right? Which in geometric sense has one extra parameter, because in geometry, right, to draw a line, you just need two parameters, right? Whereas here, you will have the W transpose, so W will have two elements and then B, so there are three. So that's why there's a little confusion there, right? But what you need to understand is that when we do the training, we won't start with any line. In the training part, we will learn the line directly, and then the margin will just be the symmetric values or opposite. And it will turn out that if your margin is not the biggest margin you will get is when the line is right in the middle. Because if you're slightly here or there, then because we assume that our margin is symmetric, your margin will be thinner than what it could be, right? So that is the point. All right, any other questions? All right, so I guess in last class I was a little sort of off my game, so I'm going to sort of revisit the topics that we talked about last time, but starting from here, right, on the slides, which is the optimization formulations. At this point, all of you should be comfortable with the fact or convinced that this is a correct optimization formulation for SVM, right? So what we have mentioned earlier is that in SVM, we directly try to maximize our margin. Our margin is given by 2 over the norm of W. So if W is your weight vector, then 2 divided by the magnitude of that W, which is essentially the L2 norm, is the margin. So we want to maximize it. So what we do is we flip it and say we are going to minimize this, right? Which is the same thing, that's equivalent. We add a square term here because that's easy to, when you compute the derivatives and everything, a square is easier than just the value. So this is sort of equivalent to maximizing the margin. However, what we also do is we also want to have these constraints, because what we want is a line that makes 0 errors on your training data, right? So there are n constraints, and if you look at these constraints closely, each one of these constraints essentially says that every training data point is on the correct side of this decision boundary, actually, or the correct side of the margin, because we also want to keep them out of the margin, right? So if you look at this, essentially what happens is that if you have a positive point, now here in this formulation, we are assuming that your yn, which is your label, is either 1 or -1. So that's different from logistic regression, where we said it's either 0 or 1, but you can always convert it into 1 and -1. So here essentially each constraint says that your training data point is on the correct side of the margin, all right? So if it's a positive point, then yn will be +1. So this constraint means that W transpose Xn plus B is greater than 1. And if it's a negative point, then W transpose xn plus b should be less than -1, right? So it's on the right side of the margin. So this is a little different formulation than logistic regression or perceptron, where the error term, the main term was actually computed using error. Remember, so our error was the square loss or logistic loss or whatever, right? But here it's slightly different, and the W came in sort of the regularization side. But here what we are trying to do is we are saying, let's try to minimize our W, which last class I also mentioned that this essentially is like a regularization as well, right? It's same as a ridge regression, but with these constraints. So we have flipped the problem a little bit, all right? So this should be clear to all of you. If not, just ask me now, right? So if you look at this problem is not a typical minimization problem because there are constraints in this, right? So we call it a constrained optimization problem, and in fact it has n constraints where you have n training data examples, and each one of them is an inequality constraint, right? So we have n inequality constraints with and an optimization formulation here which is quadratic, which is convex, right? Because it has a square term in that. Now, so what we want to do is we want to find a solution. We want to find a W that minimizes this value, but it also satisfies these constraints, right? If there were no constraints, then the answer for this would just be all zeros, right? That's the minimum value that you can get for this objective function, but that would not necessarily satisfy all of these constraints, right? Another thing that you'll notice here is that if the data is not linearly separable, then this formulation will never converge. I mean, this, if you, I mean, there are a lot of off-the-shelf packages that you can use to solve this, right? But they will not converge if your data is not separable. The reason is that if the data is not separable, that means that there is no single W. There is no line, one line, which satisfies all of them, right? There would be, so let's say you have a training data set in which there's one point like out of whack, like somewhere else. So for that point, it will not satisfy these constraints, right? Which means that this formulation will work only if your data is linearly separable, if there is a line to separate it. Later on, we will relax this assumption. We'll say, let's try to learn this when data is not necessarily separable, but here we're assuming that it is separable because of these constraints, all right? Any questions? Yes, go ahead. Uh-huh. Yeah. Will give you the predicted yn, right? And yn is the true yn. So there are two y. So this value here will give you what is the prediction, and this will give you the actual value. So they multiplied together have to be always greater than 1 because that's our assumption. All right? Okay, so that was the second point I wanted to make. Now the third thing is, as I mentioned earlier, is that you can actually stop here because there are a lot of these programs that you can use to solve it. But what the researchers realized is that you can solve this in a much better way, just instead of just using these packages, all right? So to do this, we need to understand how to solve constrained optimization problems, okay? So I'm going to take a quick detour. I started doing it last time, but let's do it again. So let's say this is a very standard optimization problem, which is unconstrained. So you want to find the value of x and y, which minimize this fxy, right? So this is easy, right? You can compute the partial derivatives of this with respect to x and y, set them to 0, and get the value, right? Very, very straightforward. Now comes a slight different version where your fxy is still the same, but you have introduced a constraint here. You're saying your fx, you want to minimize this f of x y, but your solution should satisfy this constraint, which means that any solution that you get, the x and y should sum up to 1, right? That's the idea. So how do we solve this problem? Because if you just solve this, it might not necessarily satisfy these constraints, right? So to solve these kind of problems, and then later on we'll also extend it to the case where these constraints could be inequality, right? Which is a more interesting case. But in general, to solve these kind of problems, there is this method of Lagrangian multipliers, right? So solving constrained optimization problem, right? So the first example is that let's say fx is 2 minus x square minus 2y square, and there's a subject to constraint which is x plus y minus 1 equals 0. So what the Lagrangian method says is that you can create a new objective function which is Lx, well, it's fx comma y, sorry, and you have a new unknown variable beta here, and this is equal to fxy plus beta times hxy. So this is a new objective function, but this is an unconstrained problem now, right? Because there are no constraints anymore. So beta is known as objective function. And then what the Lagrangian method says is that now you can compute the partial derivative of this L with respect to x, set it to 0. You can compute it with respect to y, set it to 0, and compute with respect to beta and set it to 0. And so now you'll have 3 equations and 3 unknowns. You have x, y, and beta. So you'll have 3 equations, 3 unknowns. We know how to solve that if it's linear system. But in general, you can, at least there is some way to solve it, right? So for example, in this particular example, this will give us, because now our L for this example will be 2 minus x square minus 2y square, right? Plus beta times x plus y minus 1, right? So now this quantity will be minus 2x, right? Plus beta equal to 0. This one will be minus 4y plus beta equal to 0. And this one will be x plus y minus 1 equal to 0, which is actually the constraint. So in an equality case, it's kind of it doesn't look like it's doing much. But anyway, so now you can solve for this, right? You can, let's say, I'll just say x, let's say, so I'd say x is equal to beta by 2, y is equal to beta by 4, right? And x plus y is equal to 1. So 3 beta by 4 is equal to 1 implies that beta equal to 4 by 3, right? And then x will be just 4 by 6, and y is equal to 4 by 12. So this is the answer, right? So basically what this Lagrangian method says is that if you convert your original constraint problem into an unconstrained problem by introducing a Lagrangian multiplier beta, and then if you solve that, then the solution that you will get is the same as solving the constraint problem, all right? So this makes sense, right? And in general, if you have many constraints instead of just one, if you had h1, h2, h3, however many, right? All you do is you just introduce those many Lagrangian multipliers and just keep adding it here, right? And then you solve for this, and this should give you the answer. Somebody had asked me last time if there is any constraint on beta, and it's not. The beta can be anything, because anyway in the end beta is going to be multiplied with h of xy, and if it satisfies this equality constraint, then this will be 0, right? So the effect of beta will go away. So but this is the sort of the straightforward method, all right? Any questions so far? All right. And then in the slides I have one more sort of problem that you can go and try to solve, which is what if you have multiple constraints, right? So let's say you have a function which is a function of 3 unknowns, and you want to find the value of x, y, z that minimize this, and you have 2 constraints here, right? Then you can introduce 2 betas, just add it to that, try to solve it, right? Here you will see that solving this might be a little more tricky because your constraints are not linear, all right? So later on I'll mention this again, but this is a nonlinear constraint, right? But typically a lot of the optimization solutions that are out there, they assume that all your constraints are linear. In fact, they call them affine. So affine is just another term for a linear constraint, right? So then things are easier, because think of it this way, right? So you have some function, right? So each one of these constraints are basically drawing a line and saying, if these are equality constraints, you're saying, I'm going to draw all these lines and I want my function, whatever solution, to lie on those lines, right? So if you have 2 lines, then you want your function to lie on the intersection of those lines and so on, right? So that is the idea. Okay, so now so this is sort of general formulation. Now comes an interesting question where we say that our constraint is actually inequality. Right? Now things become a little more interesting because we want to find a solution to this optimization problem which satisfies this constraint. So going with that similar example as before, think of this function as a function of x and y, right? And then what you're saying is that I want to find the value that maximizes this function, but it should not be under a certain line. That line is given by this. In fact, this is not a line, right? This is actually a quadratic constraint. So what you're saying is that there's a curve in x, and I want it to be above that or under that, in this case under, right? But that is the idea. So how do you solve this kind of problem? So Lagrangian constraint again works here as well. So what you do is that you introduce constraint just like we did Lagrangian multipliers, just like we did in the equality case. Here we are going to denote them by alpha, and then we are going to say, we are going to convert it. Okay, let me write it out here. So this was equality constraint. So let's say we are considering the case of inequality constraints. Let's say you have some function f of xy is x cubed plus y square, and you want to minimize that. So you want to find minimum, you want to find x and y that minimizes that, subject to constraint of g of x is that x plus y is less than 7, right, or something like that, or less than equal to 7. So first thing what you do is you say you convert them into this form, right? If you have a greater than sign, you can always put a negative sign and try to bring it here. But let's say all of our constraints look like this. Then what you can do is you can introduce a new Lagrangian function, which is a function of x, y, and alpha. I'm using alpha just to differentiate between equality and inequality, but these are just scalar values. And this is given by f of xy plus alpha of g of xy, right? So now we solve this, but here we put an extra constraint that alpha is positive. So this is not as straightforward as an equality case. Here we're saying let's try to solve this subject to this, but this is a sort of an easier constraint because this is just alpha needs to be positive, right? Those we can do by introducing things like logs and stuff. So if I put log of alpha, then because log anything below 0 is not defined, so you can do those things. So those are known methods of log barriers. So but for now, let's assume that this kind of objective function is easier to compute. So what we have done is we have converted a inequality constraint optimization formulation into this simpler formulation that we can compute. Okay, any questions so far? So in the handouts, I actually have worked out a solution which is right. So you can look at it in the handouts. I have a solution for this problem that was on the slides. This problem that was on the slides, you can see how to solve it, right? So, but for us, what we want to talk about is a more interesting case. Well, this is a general case, right? So this is a general case in which you have both type of constraints. You have some equality constraints, you have some inequality constraints. You can solve this by creating this large Lagrangian. So let's say your unknowns are this W. Let's say because now we are going to talk about SVMs. So let's say W is your vector of all unknowns, and your function is a function of this W. You want to minimize this subject to all of these constraints. You can create this Lagrangian where you have your f of W already there, plus you add some Lagrangian multipliers that correspond to your inequality constraints and Lagrangian multipliers that correspond to your equality constraints, and then you solve this subject to this constraint that all your alphas need to be positive, right? Not betas, just alphas. Okay, any questions so far? All right, so now let's see. So now let's go. We are going to take another step towards this notion of primal and dual formulations of optimization problems. So let's look at this particular, so we are just moving from this setup, right? So let's say this is what we want to solve, right? So I'm going to first define this sub-problem, theta p, okay? This theta p is a problem in which we want to find the alpha and beta which maximize your L, right? So we are not worrying about W. So we are saying let's ignore W. For any W, can we find the alpha and beta, and all the alpha should be positive, which maximize this, right? This is not what we want eventually, but this is a part of it, right? So theta p of W is the value that your function takes such over all alpha and beta, right? So we have ignored W, and we are saying, okay, over all alpha betas and all alpha should be positive, what is the value of L, right? And then what we do is we try to minimize that over all W. Okay, so we are doing first taking the max over all alpha beta, and then we are trying to minimize that for all W. And what you can see is, or what I'll show you, is that the solution to this, which we denote as P star, will be the same as solving this equation. All right, so this is the primal formulation. So the idea is that we want to find the solution, we want to find W, alpha, and beta that minimize this whole thing, right? And what we can do is we can first maximize over all alpha and beta, and then minimize over that function for all W, and the solution that you get will be the same as if you were solving the optimization, the constraint problem. So just to make that point a little more clear, right, so this is what it is, right? So we are defining theta p of W, right? So this is just a function of W, is a max over all alpha beta subject to that all alpha i's are positive, right? L of W alpha beta, right? So this is our sub problem that I'm just defining here, right? Which will be same as max of alpha beta alpha I greater than equal to 0, because this is nothing but f of W plus, now let's say this alpha and beta are vectors, right? So they contain all their multipliers. So this will be alpha I times G of whatever W. So this is all our constraints, all our inequality constraints, plus beta I H of I W. So these are all our equality constraints. So these are inequality, equality, right? So this is what we are trying to find over all alpha and beta, right? One thing you can see is that this part does not depend on alpha beta, so this will be same as f of W, whatever W it is, plus max alpha beta, this summation. Right? And now if we want to find this, the min of this value, min of theta p W over all W, right? And if I define that as P star, the W that you will get by solving this, well, actually the value of this function that you will get by finding the minimum W, right? So this is nothing but min over all W max over all alpha beta LW alpha beta, right? Because that's how we define our theta p, right? And it turns out that if you solve this equation, all right, so this is still an optimization problem, two optimization problems, one after another. First you maximize, then you minimize. Solving for P star is same as solving the constrained optimization problem. Now I could give you a detailed proof, but that will take too long. But the point is that if you think about this, right, this formulation over here. So if you find the solution, right, what you will see is that your theta p of w right. So if theta p of w, right, it will be same as f of w, right, if all constraints are satisfied. Right? If I solve for this theta pw, right, if I know how to solve it, right, and if I solve this, what will happen is that if all of these constraints are satisfied, if gi's and all hi's are satisfied, then this theta p of w will be just f of w. And if not, else it will be infinity, right? Because if these constraints are not satisfied, right, if let's say this is not equal to 0, then I can arbitrarily make my beta I very high or very large, right, and make this value, because I want to maximize this, right? So if this constraint is not satisfied, this is not equal to 0, then I can make my beta I so large that this value will become infinity, because I want to maximize this whole thing anyway, right? Which means that in that case this will be infinity. And let's say if any of this inequality constraint is not satisfied, which means that gi of w is actually greater than 0, right? It's not satisfying the constraint. Then what will happen is that and since I can only make my alphas positive, then I can make my alpha again very large, and this value can become very large and it will become infinite, right? Which means that if we solve for this whole problem, satisfying all of these constraints, then the solution that we get will be same as solving for the optimization problem. Otherwise, this will be infinite. All right, so that is sort of a quick proof. For detailed proof, we can talk, sort of outside this class. But the thing that you want to notice is that this min-max problem is same as solving the original problem. Now what we will show is that if we flip this problem and try to first solve the min and then max, if I make it a max-min problem, then it becomes a slightly different problem, right? So let's define a slightly different problem. Theta d, all right? I'm going to define theta d of alpha comma b beta as min over all w L of w alpha beta. Because I flipped it around, and then what I'm going to do is I'm going to say let d star be the value of this over all alpha beta max of this theta d alpha. So I've flipped it around. What I'm saying is that I'm defining a new problem, which is I first find the min of L of this value over all w, and then finding the max of that, all right? So that is d star. So this is known as a dual problem. So this is another problem that you want to optimize, right? So this is called the dual optimization problem. So the first one is what we call the primal optimization problem, because this is same as max of alpha beta alpha I greater than equal to 0 min, just replacing that over all w. So here is the difference. This is what we call primal, because this, as I showed you earlier, is same as solving the original problem, right? So if you solve this series of optimization problems, first find the max, then find the min, right? That will be exactly same as solving the original problem, so we can do that. However, if we redefine our problem like this is a different optimization problem, where we first find the min over w and then find the max over all alpha betas. That is called the dual optimization problem, right? But the w that you will get from each one of them, see, each one of them will give you some w that is maximize or minimize this thing, need not be the same, right? In fact, what has been shown is that this d star, right, the value of your objective function after you have done min and then max, will always be less than equal to p star. This is also known as, I think, as the weak duality problem, the weak duality theorem. Okay, that the d star that you get will always be less than p star, right? And this is also sometimes also known as the min-max theorem, which basically says that if you have two functions, if you have a function of two parameters, x, y, right, or something else, overload this. Let's say you have a function of z w. Right? What this says is that if I first take max of fzw over all w, okay, and then I take a min over all z of this quantity, this will always be greater than equal to if I first took the min over all z and then took a max over all w. This, I think, John von Neumann sort of talked about this long time back, and then this is also used in game theory. In fact, John Nash, when he won the Nobel Prize for his game theory work, it was sort of started from min-max theorem. Then he showed other things. Basically, if you have two players playing games, then one is trying to minimize, one is trying to maximize. So he showed sort of interesting results, but all kind of arises out of this, right? So if you first take a max, then take a min, that will always be greater than if you first took a min and then took a max. So min max is greater than max min, and it's not too tricky to show why this is true, right? So for example, we can show that very quickly. Let gz, all right, let's say gw is equal to min over all z f of zw. Let's just define this new function in which we have sort of taken a min over all z, right? Then of course g of will always be less than equal to f of z comma w, right? Because this is the min, so it will always for any z. And then you can say that max of this, max over all z, so max over all w of g of w, right, will always be less than equal to max of w over fz of w, because the inside was always less, right? And then, and this is nothing but max of w min of z g of w, right? Oh, sorry, f of x comma w. So this is, I just replace this with this value, right? And this will be always less than equal to max of w f of z comma w, right? Now what you can see is that this quantity, right? This quantity, so max of w over f z comma w will always be greater than equal to if I took a min outside, right? So that, because the minimum value that will be, that this could take over all z will always be less than this value, right? So this will be max of w z comma w, right? Implies that you can then put it here, because this value is always greater than this and less than that value, which means that max of w min z f of z comma w will always be less than equal to min z max w f z comma w. I mean, look at it, later on, more leisure time. But the idea is that min-max theorem tells you is that if you took max first and then min, that will be greater than if you took min first and max later, right? But the main thing we want to talk about is that here, because of all of this min-max theorem, this is true, that if you solve the dual problem, which is you first took the min, then you took the max, then the solution that you will get will be less than or equal to if you solve the primal problem. Now the question is why you want to do that, right? Why not just solve the primal problem? The answer for that is that sometimes the dual problem is easier to solve. All right, and in fact in support vector machines we will see that by solving the dual problem we actually get a lot of interesting artifacts which makes our support vector machine learning very efficient. So that will become clear a little later. But the reason we are going from primal to dual is two reasons. One, it becomes easier, and which is true for any problem, and second is that it gives us some interesting artifacts that let us make our support vector machine learning more tractable. Okay. However, there's another point that I want to make is that what this dual thing tells you is that D star is always less than equal to P star, right here. But which means there is an equality sign here. So which means there is some cases where this could be the same, right? If they're not the same, and if you solve the dual problem and you say, hey, here is W that I get by solving the dual problem, then it's not necessary that it will be the same W that you would get by solving the primal problem. That is called the duality gap, right? So if your duality gap is large, it means that if you solve your primal problem, if you had solved your primal problem, then the answer that you would get would be much different than if you had solved the dual problem, right? So even if you convert your optimization problem into a dual problem, it's not necessary that you'll get good results, even though it might be easier to do, right? But there are certain cases when both of them are the same, right? That's called strong duality. And for that, some things need to hold true. There are two conditions. One is that your F should be convex, all right? Convex means that, you know, it should have only one minima or maxima. And the second is that your constraint should be affine. I mentioned that earlier. Affine just means they should be written in a linear form. So it should be some ax plus by less than equal to 1, things like that. There should not be any non-linear terms in it. If that is true, then this would be equal, right? Which means that if you look back at our support vector machine formulation, optimization here, right? This is certainly convex in W, right? Because it's a parabola if you think about it. And all of these constraints are linear in your W, right? You're just taking W and multiplying them with some scalar values, which means that in this case, if instead of solving the primal, if you solve the dual Lagrangian formulation, the answer that you get will be the same. That means that you can actually go ahead and solve the dual problem. But in future, when you're doing, let's say you're going into machine learning research, you will come into situations where you would have some other optimization problem, and you might want to convert it into dual form. The thing that you need to check is that is the gap 0, which means D star equal to P star, or if you can at least show that the gap is very small. Sometimes they talk about this weak duality. They say, you know, I cannot show that these both are same, which means that my f of W is not necessarily convex, or maybe my constraints are non-linear. But as long as I can show that this gap is small, that means D star minus P star is small, then you can say whatever answer I get by solving dual optimization problem can be used as a proxy for the primal formulation. Any questions? All right. I'm sorry, go ahead. Right. Right, so that's a good point. So what Ritwik has noticed is that in our original constraint formulation, right, there is no B here, but B is over here. So B is still a variable, but what it will mean is that when we solve for our F, right, when we convert it to a dual Lagrangian, right, B will need some special way to solve. So B would not be as straightforward as solving for these individual W's, but there is way to do that. So we'll come to that. But B is a variable, even though it does not occur in the objective function, it does occur in our constraints. So it will have some effect. You cannot have any arbitrary B, essentially. Any other questions? Yes.
Why is D star easier to solve?
So it's not necessary. The question is, why is or the dual problem easier to solve than primal? That's not always true, but in some cases it might be, and we'll see in SVMs it is, and because of that we do that, but it's not a law, right? So in some cases you might be better off just solving the primal. It might be easier. But if you look at this, right, so in primal, what you do is you first figure out what is alpha beta, right? You first try to minimize this problem, maximize this problem with respect to your alpha and beta, right? And then whatever you get, you try to minimize that. And in dual, you do the opposite. You first try to minimize this with respect to W and then with alpha beta. Now, since in many cases alpha betas get multiplied with your constraints, right? And your constraints, if you assume, are affine, which means they are linear, then this would be slightly easier to solve. So once you, here what you do is you ignore alpha beta. You say alpha betas are just constants, and you solve for W. It's easier because it's a convex function if you're assuming it's convex, right? So it will be slightly easier, and then this will be sort of little easier. So that's the, I mean, a very vague reason, but it might not always hold true. But what we'll see in the case of support vector machines is that that's what will happen. All right. So anyway, so this is the idea, right? So in general, D star is less than or equal to P star, but for the SVM problem, the strong duality holds. And what that means is that there are certain conditions that need to be true, all right? I mentioned it last time. So whenever we say that there is an objective function, right, and this is the solution, right, what are the things that need to be true? So those conditions are known as KKT conditions or Karun-Cohn-Tucker conditions. Essentially, it's very easy, right? So let's say I give you an unconstrained problem and I say this is the solution, right? This will be a solution if the partial derivative of that function for those values is 0, right? That's how we do our optimization. So basically what KKT conditions say is they just list them out as our constraint, as sort of sufficient condition. So for example, this is nothing but the condition that we use to solve our optimization, right? That the partial derivative of your objective function at W is 0. That's true. The partial derivative of your objective function with respect to all of your betas will be 0, right? Because that's how we define it. All of your alphas are greater than or equal to 0. That's our constraint. All of these constraints should be met, which is G, because this is the inequality constraint. So this should be true, right? And all of, I think I didn't list the equality constraints, but all of your equality constraints should also hold, right? And then the last thing is that this should be true. So the alpha I that you get by solving this formulation, either primal or dual, it will give you the same answer. The alpha I that you get, when you multiply it with the constraint value at the optimal function, that should be 0. This is known as this is one special constraint or special condition in KKT that comes only when primal is equal to dual. So I'm not going to jump into how to derive this particular one because this is not straightforward. All it's saying is that whatever solution that you get, either alpha I should be 0 or this value should be 0. That's the point. All right. So together they should be, when you multiply them, it should be equal to 0. The reason I'm talking about this is that this becomes very essential in our whole support vector machine formulation, and we'll come back to that. But anyway, so this is the KKT conditions that need to hold if this is true. So KKT condition, this is again a detour, right? So what happens is that if you have an optimization problem, it could be constrained, unconstrained, whatever, and somebody comes and says, this is the solution. This is the W, let's say it is a function of W. Then somebody says this W is the one that optimizes this. What you can do is you can take the KKT conditions and see if it is true for all of them. All right, and so that is why what we say is the KKT conditions are the necessary conditions for this to be true. And if your function is convex, what happens is that you can take the KKT conditions, solve for those, and the W that you get will optimize your F, right? So which means that KKT conditions are also sufficient, right? So for convex functions, KKT conditions are necessary and sufficient. But for general non-convex ones, or in general setting, they are at least necessary. So that is the idea, right? So this is what our relationship between primal and dual is. So the main point is that we had an optimization problem in SVM, and we showed that we can convert it into a Lagrangian formulation by using Lagrangian multipliers. Then we showed that we can solve it in two steps. First, find the max, then the min, right? Max over Lagrangian multipliers and then the min, and that is the primal formulation. Then we showed that that is same as solving the dual formulation in which we do the other way around, and that will give you the same answer. All right, but it's still, we are still not clear how to solve it, right? So we have said that we can solve this, but we still don't know how to solve it, right? Any questions so far? All right, so now let's write out our, come back to this one. So remember, this is our objective function. This is what f of w have been talking about, and these are all of our hi's, right? GI's, the inequality constraints. In this formulation, there is no equality constraint. That means there will not be any betas. They'll just be alphas. So let's do a simple toy example. Let's say we had we had our data in two-dimensional space, right? So there is one w, w1, w2 that defines our hyperplane, right? And then there's a b on the side. And we have, let's say we have only two training data points. One is 1, 1, x1, and the label is -1, and 2, 2, label is +1. So what you can do here is that you can write out the optimization problem here, right? So what we want to do is we want to minimize this f of w for, which is this, subject to these two constraints, right? There are only two constraints because we have only two training data points. So you can actually solve this by hand, right? So what you can do is you can say, hey, let me sort of rewrite these like this, and then let's try to let me try to do it here. Lost my pen. Here it is. Okay, we have 3 minutes. Let's try to do it. All right, so what we are saying is minimize overall w, f of w, which is just w square over 2, which can be written as w1 square plus w2 square over 2, right? Subject to two constraints, because you have two training data points, and which basically say that y1 w transpose x1 plus b minus 1 is greater than or equal to 0. That means that it's on the right side of the margin. And y2. The reason we are doing it by hand is because we have only two data points, right? Now remember, my x1 was 1, 1, and y1 was -1, and x2 was 2, 2, and y2 was +1, right? So I can rewrite these. I can say this is nothing but saying that w transpose x1 plus b minus 1 is greater than or equal to 0, or minus of this, right? Because y1 is -1. And this one is w transpose x2 plus b minus 1 is greater than or equal to 0, right? And we can, now x1 is 1, 1, so we can also rewrite it. So they become same as subject to minus w1. I'm going to open it and multiply it with 1, 1. So w1 minus w2 minus b minus 1 is greater than or equal to 0, right? And this one will be 2w1 plus 2w2 plus b minus 1 is greater than or equal to 0, right? So it becomes a slightly simpler formulation. Then what we can do is we can now define our L, which is our Lagrangian, by introducing, now there will be two constraints here, right? So L will be same as w1 square plus w2 square over 2 plus alpha 1, the first one, times minus w1 minus w2 minus b minus 1 plus alpha 2 times 2w1 plus 2w2 plus b minus 1. Right, now we want to solve for this, right? So what we can do is we can compute the partial derivative of this with respect to w1, w2, alpha 1 and alpha 2. So dl by dw1 will be equal to just w1, right, minus alpha 1 plus 2 alpha 2, this is equal to 0, right? And then dl by dw2 will be equal to same, W2 minus alpha 1 plus 2 alpha 2 equal to 0. It's very symmetric. And then dl over d alpha 1 will be just minus w1 minus w2 minus b minus 1 equal to 0. And dlt alpha 2 will be equal to 2w1 plus 2w2 plus b minus 1 equal to 0, right? So here's the whole thing. And now what you could do is you can solve for all of this. And then there is also a subject to here, that all your alpha 1 and alpha 2 are greater than equal to 0. So if you solve for this, what you will get is w1 is equal to w2 is equal to 1 and b is equal to minus 3. And the alpha 1 and alpha 2 that you'll get are greater than 0. So here it will work out. So this is the solution that you get, right? So you can solve the primal optimization problem by hand if you have 2 data points, right? But if you have n, where n is very large, then solving for this becomes a big nuisance, right? So to do that, we will sort of go the dual route. We'll first convert into a dual problem and then try to solve that. So we'll look at the exact formulation and how it happens in the next class. Any questions so far? All right, thank you very much. I'll see you on Wednesday.